Hey guys! Okay, so it's time to apply what we've learned so far. Today, we're looking at a real-world application of quantum mechanics by studying quantum computers. Where do I even start with this one? I guess we can talk about normal computers first, and then relate them to their quantum counterparts. So all data on the computer, storage, communication, transferal, is done through a series of bits. A bit, short for binary digit, is the basic unit of information in computing and digital communications. The information transmitted during communication is stored in a series or chain of bits. The more complicated the transmission, the more bits are needed for the process. Bits are often represented as either a 1 or a 0, also known as true or false, respectively. Each bit can only exist in one of the two states at any given time. This means that no matter the computer's speed or capacity, the bits used are only available one at a time. In other words, if we ask the computer to solve a maze, it can only check one path at a time before eventually coming across the completion. This is where quantum computers come in. The quantum computers utilize properties we've discussed throughout the series so far, primarily entanglement and superposition. The quantum computers use qubits, short for quantum bits, the counterpart to the basic unit of information in computing. These qubits will not only be a 1 or a 0 like the normal bit, but they can also be in any superposition of the states. Since they can be in multiple states at once, they are capable of much more than a normal bit. They can calculate information much faster and require exponentially less qubits to perform the same calculation that a normal bit series can. Let's go back to the maze, now with a quantum computer. The quantum computer will calculate the same maze successfully at the square root of the time that a classical computer can. As you can imagine, though this is not much of a difference with a small maze, a big one will show that quantum computers are much more efficient and practical than a classical one. The maze represents calculations, basically. With more complicated logic systems and more information transfer, quantum computing becomes more and more useful. So why do they work so well? Well, we already talked about how qubits are in a superposition of the states. Now, entanglement is used to help interpret the information on the qubits. In previous videos, we talked about how looking at the state of a quantum system forces it to choose one solid state at random instead of remaining in superposition. However, if the qubits are entangled with another set of particles, we can get the computer to read and interpret the information from the other set, removing the disruption of the original qubits. And since quantum superposition can only be predicted by probability, there's a chance that the read information will actually be reading the wrong state of the qubits. If we can successfully implement quantum entanglement, however, we are able to reduce or remove the probability of a misfire. So, it's weird, really. Quantum computing is an answer to speed and capacity, but it's also a problem concerning the side effects of quantum mechanics, yet even then it's also the answer to its own problem by also using quantum mechanics. We are just scratching the surface of the quantum computing world, but as time and technology progresses, both the need for quantum computers and the progress in the field are expanding. It's an exciting age, making technology exponentially more powerful than it has ever been before. Unfortunately, that's all the time I have for today. I hope you guys are enjoying the series. Thanks so much for watching. Hope to see you all next time.